some kind of fundamentals of computing, because obviously anything that you do these days handling large amounts of sequence data or protein structure data or whatever, you need to use computers to handle those data. So with the sequencing data that you're going to be generating, you're going to need to use computer software to analyze that. You're going to have to try to automate some of that processing, and you're going to want to keep track of what you're doing. Now, the de facto standard for doing all this sort of thing is not Windows, and it's not a Mac. It's usually a Linux-based system. So I'm going to tell you a bit about computers, sort of fundamentals of computing and sort of operating systems, and kind of things where sort of Windows and Linux and things all diverge, and why that happens, and also then take you into some fundamentals of programming, which you're going to come back to with sessions from Mike later on. And then after we've done the lecture, we're going to do a sort of workshop of learning to use the command line, because what you're probably used to is point and click on everything. It's a really inefficient way of doing things when you've got lots of data to handle. So we're going to have a look at using the command line to do that sort of thing instead. So to kick off, we're going to spend, as I said, about an hour or so covering basic computer concepts, computer hardware, operating systems, databases, algorithms, a bit on programming, and using the command line. So, basic concepts, and some of this may be blindingly obvious to most of you, but I have encountered people who really don't grasp what they're doing with a computer. So, we have basically four kind of major concepts. We have data, and these are some examples of data files. So, a bit small and a bit blurred, but this is a typical DNA sequence file. It's got numbers down this side and A, T, C's and G's going across. This is a PDB file containing information about a protein structure. We'll look at some of those a bit later on. And this is a header from a Swiss prop file giving you information about protein sequences. This is kind of all the annotation that goes with it in terms of authors, all that sort of thing. Those are all data files, as is that, which is kind of pretty meaningless, and it's kind of encoded in a way that the computer can understand, but you can't. So the sort of concept there that you're probably most familiar with is things like zip files. So when you've gathered together a set of files into a folder and you've zipped it up and compressed it, you can't read what the content is without unzipping it again. But if you looked at one of those files, it probably looks something like this. So that's the first idea is data. And the second idea is a program that we'd use to process those data. And I've found in the past that people can be confused between the difference between these things, because you're so used to, say, having a Word document and just clicking on it, that you don't realise that what happens when you click on it is that that document type is associated with a program, Word. It opens that program, Word, and it loads that file in. And it all happens just through that double click. So programs mean writing some code, and we'll come on to some basics of that later on. This is a program written in C, one of a number of programming languages. It's a small fraction of it. This is also a program. Again, it looks like that kind of random looking data file. This is what's called a compiled program. We'll come back to that in a few minutes. And of course, things that you're used to using, like PowerPoint or just a browser for browsing through different folders on your computer. Those are all programs that are running. Another important concept then is a database. Those of you who've done, well, you've all done BIOC 2001, where I talked about databases and data banks, and the concept that a data bank is just a collection of flat files of data. So the sorts of things that we saw, oops, I've just done too many, saw here. So things like this would be part of a data bank, whereas a database is hidden behind some interface, some single piece of software that you can use for viewing it. So that might be a web interface like this, which allows you to access information, searching, and so on. Or it may be what we call a relational database, written in a particular programming language called SQL, which again we'll touch back on in a few minutes. This is a way of storing data and allowing you to extract it and pull information out. And that's just a snippet of SQL. And then the other thing, of course, that you're familiar with is actually visualizing data. So looking at protein structures, looking at sequence alignments, and so on. That sequence alignment is actually displayed with a piece of software that I wrote, which allows you to embed sequence alignment viewing into web pages. These are different renderings of the same PDB file, so a protein structure file of an antibody Fab fragment binding to lysozyme up at the top here. So here you've got a just a stick model, here you've got cartoons, and here you've got space filling. So different ways of interpreting the same piece of data. Now, taking that concept one step further, basically what you tend to do is start with data, you pass it through a program, and you may get some sort of visual output, which might be something very pretty, or something just other plain text, which of course is a data file, which you could then enter into some other program. So, unlike with the association between a Word document and the Word program, where basically you double click on your Word document, it fires up Word, you see the visual interpretation of the data file that's associated with it, we can actually generalize that much more. In terms of Word, you might decide to use OpenOffice or LibreOffice instead of using Word to read that document. In this case, we're taking a PDB file, a representation of a protein structure, and here we're using Rasmol or PyMol or something like that to get a visual view of the structure. But here we're using another program, program of mine called PDB to PIR, which takes your structure file and extracts the sequence information from it and displays that in a format called PIR. So it's just showing the one letter code sequence with a header at the top and each chain terminated with a star. So that's quite a sort of important fundamental concept, that you can start with a single data file and you can use different programs to analyze those data in different ways and produce different representations of the information. So that then brings us on to computer hardware. So obviously these days people are familiar with computers either in their watches or their phones or laptops or maybe desktops like these. But in the good old days, computers looked like this. These are sort of proper computers. I mean, I guess judging by the clothing, this is sort of early 1970s. This lady here carrying this sort of box. These are about this big, not this thick. This is a disk. with probably about 10 kilobytes capacity. So, it's like, well, virtually nothing really. And to load these in, you had a sort of drawer in this thing that looked a bit like a washing machine. Pull the drawer out, put the disk pack in there, push it closed, and you could read the data. Of course, people also kept data on tapes. So there's tape machines there, reels of tape about this big. Tape was about sort of, 3/4 of an inch wide, something like that. So this kind of predates my computing a bit, but we actually, when I was doing my PhD, we still had one of these disk pack machines, and there was one person in the department still using it. And we certainly used tapes as a way of storing data like that. This is a slightly newer setup. This was kind of around about the sort of machine that was just being retired when I was doing my PhD. Before discs and tapes, people used paper tape. So, this was kind of really the technology of the 1950s, I guess, into the 60s. But as recently as, about 1993 or so, the National Grid company, who look after electricity distribution, were still using computers booted from paper tapes like this. Because I had a little period out of science and doing programming for a living, and I was helping write some software which replaced these machines. There was two machines about as long as from here to that wall, and about that wide, which basically were identical, ran the same software in parallel. In case one of them blew up, the other one could carry on. But when they had to be restarted, they had to be started off paper tape like this. And basically, each row, each column like this, represents one character of information. Similar sort of technology was punched cards. So I just about remember as a child having boxes of Clark's shoes, and every box of Clark's shoes had a card like this in it with basically an identifier for the shoe. So it's like an early version of a barcode, effectively. But certainly up until the late 1970s, people were programming big computers using this sort of thing. So every line of code that you wanted to type for a computer program was a punched card like this. And if you dropped the pile of cards on the floor, then your program would be in a random order. So yeah, it was not much fun. These old computers, this is what memory looked like on old computers. It's called core memory because this is a little close-up of a corner of this. I don't know if you can see, but it's little donuts of sort of ferrite material, sort of magnetic or magnetizable material. And these little rings are called cores. So the whole thing was called core memory, and basically just had these wires threaded up and down through them. And this was what you would use for your storing your program as it was running and storing data and so on. But obviously a tiny amount of memory in each of these. And each of these things is probably about an inch square, something like that. Now this is getting on more to the sort of time when I was doing my PhD. That's not me sitting on the top of a computer, but these digital equipment, DEC computers, were what I used during my PhD, and we did use these tapes for storing data. This is also the days when floppy disks, which probably none of you use anymore because you just use USB sticks, but some computers still have 3.5-inch disk slots. Before those firm disks, this was the sort of thing people used, and they really were floppy. So these are 5 1/4-inch discs or 8-inch discs there. And I really do recommend a trip to the National Museum of Computing at Bletchley Park. So Bletchley Park is famous for the decoding of the wartime messages, but actually more interesting than the Bletchley Park bit itself is one of the huts around the back, where they have this National Museum of Computing, basically a collection of old, almost exclusively British computers, and you can see all this sort of kit that I've been showing you. These days, of course, this is a fairly big computer, and whether you're talking about a laptop or a desktop, the components inside are essentially the same. You have some sort of motherboard, which everything else kind of plugs into. You have a CPU, which is the actual processor which really does the work, and that's where all the huge advances really in computing power have come from, is improving those. You also have the memory. This is a typical sort of memory chip, which has replaced those cores. Again, we have huge amounts of memory in a computer now, typically a minimum of 2 gigabytes. The first computer that I had as a home computer had 1 kilobyte of memory, which was shared between writing the program and the screen. So as your program got longer, the amount of screen available for displaying something got smaller. It was quite bizarre. And also the screen went blank when it was actually doing any calculations. It only showed you something when it was waiting for you to enter something. Still managed to write a mastermind game for it though. Then you might have a sound card, sorry, a graphics card, that is, in this case quite a powerful one. It's got its own fan to cool it down. This is then a network card for connecting to cabled network, a sound card, a hard disk for storing data and storing programs, and that's something people often make a mistake. They say their computer's running out of memory when they actually mean it's running out of hard disk space. So this is memory, this is disk. So that's your long-term storage. This is what's used when you're actually running a program. And then maybe some sort of optical disc, like a DVD or CD or something, and maybe even one of these older floppy disks. Often, even in desktop computers, these components are all combined into one. So the motherboard has a sound and graphics and networking all kind of integrated onto the motherboard. And actually, given the fact that this lot comes as one component and you then need to add maybe 1, 2, 3, 4 more bits, it's really very easy and straightforward to build your own computer. I think the cheapest one I built a few years ago was £100 for everything, including the case, motherboard and things. I think they've gone up a little bit since then, though. Okay, so having looked a bit at hardware, moving on then to operating systems. This is kind of a software layer that sits between the hardware and the actual programs that you're running. So it looks after things like the networking, the access to the internet or whatever, tools for handling files, moving them around, tools for handling, renaming files, just looking at the content of files, that sort of thing. Handles users and security, things like passwords, all that sort of thing, putting different users into different areas of disk space, defining who can install software, that sort of thing. An operating system may, but not necessarily, provide a graphical interface as well. And of course, the things that we're all familiar with, like Windows and Apple Mac, all have quite attractive graphical interfaces. Indeed, as does Linux. But with Linux, you can choose whether you want a graphical interface or not. So, if you so desire, you can go to this. It's not going to display for me. Oh, okay, it's not going to display on there. Right, we'll come back to that later because we're going to use that sort of interface later. There's just a text prompt. May include other sort of non-essential bundled tools which aren't really part of the operating system but always get delivered with it. Things like a web browser, for example. Now, there used to be lots and lots of different operating systems. So the one that I used during my PhD was VMS, which we ran on these DEC VAX computers. Our University Central computer was an ICL2988, which ran VME. They've got one of those at the Computing Museum. CPM was something that ran on kind of desktop PC type computers. And then, of course, we got things like MS-DOS, which became Windows, OS2, which was very popular for a while and then kind of died out, Amiga-DOS, which was my favourite, which ran on Commodore Amiga computers, various flavours of something called Unix, which is what Linux derives from, and then, of course, Mac OS, which runs on the Apple, which, well, in fact, Mac OS, since OS X came in, it actually is a variant of Unix. So underneath, it's Unix, but has a different and very attractive graphical interface on it. These days, we just really have the three. Windows, various different flavors of Unix and Linux, and Mac OS on OS X on Apple. So there's a bit of a tie-up between the different operating systems and the people who use them in the kind of biology world. So people in the kind of zoology, DNA, phylogeny end of things originally didn't have very much data. They had fairly small data files to deal with, so they tended to prefer Macs and Windows machines. Whereas people doing things like crystallography, handling larger amounts of protein sequence and structure data, would tend to have used these bigger kind of DEC VAX machines that I showed you earlier, which means that, and also computer scientists would tend to use that sort of thing, which means that these days people from this sort of background tend to use Mac and Windows more, and people from this sort of background tend to use Linux more. But of course, since Mac OS X now sits on top of Unix, there's a bit more use of Mac these days, but Windows really very, very little use from the protein end of things. Okay, so I said we'd come back to databases a little bit more. This is the distinction that I made in BIOC 2001 between a data bank and a database. Relational databases, as I mentioned, are the sort of core way in which we store data in order to be able to search it, pull out information. And there are lots of different ones of these. Microsoft Access is the one that people are probably most familiar with. It's another part of the Office suite. Microsoft also has a bigger, more professional version called SQL Server, SQL, or known as SQL. Oracle is probably the biggest commercial database. So if you get the train from Paddington to Reading, just before you get into Reading, on the right there is a kind of cluster of about 8 big office blocks, all of which belong to Oracle. It's one of the biggest software companies after kind of Microsoft and Apple. Sybase is another commercial one. The ones that we tend to use in the kind of academic world are MySQL and PostgreSQL, which are both free open source operating system, databases, which will run on Linux. I believe they run on Mac and Windows as well. But different people have different preferences over those two. Personally, I prefer PostgreSQL. It's a bit more advanced than MySQL, but MySQL is used very widely as well. So the idea in a relational database is that you structure your data into tables. These are also known as relations. I'm not going to go into a huge amount of detail about this, but basically the way that you take a data set and divide it into tables is quite a complex process in order to do it optimally. Needs a lot of careful thought and planning, and you go through a process known as normalization, which basically is a way of removing redundancy from your data and removing chances for errors. So that maintains data integrity. So mostly what we do is use a language called SQL. That's why lots of these things have SQL in their name, which stands for Structured Query Language. And it's a standard database query language. It's an ANSI standard, American National Standards Institute standard. So basically, it should be possible to take a database that's been written on Oracle and just take all the kind of code that stores all the information and just run it on PostgreSQL or something instead. In practice, it's not quite that simple because most of the databases actually have extensions that take you beyond the standard. So if people have used those, then obviously it doesn't work. Basically, you have 4 types of command, one of which is for creating what's called a schema, which is the layout of the table. So basically what the tables are called and what they contain. You then have commands for inserting data into the tables, commands for extracting data from the tables, and finally database management commands, which allow you to create users and grant them permissions to insert data into particular tables or pull data out of tables and so on. Also commands for creating indexes, because one very important thing when you've got a big table is that you have some way of being able to jump to the right bits of data very, very quickly. So we had an example that somebody working with me last week gave me where a query with an index switched on took 0.1 of a second, 0.2 of a second, something like that. With the index switched off, it took 4 hours. So this sort of thing is really very important. And designing the tables in the right way, designing where the indexes are, is absolutely fundamental to getting a really good, efficient database. So, as I said, I'm not going to go into more detail on databases. If any of you are doing BIOC3301 next term, then you'll get a somewhat similar lecture from me covering the same sorts of things that we looked at, but we'll go into more detail about certain points and less detail about others. So, databases is one of the things that we cover in quite a lot more detail than that. The other important concept, and this becomes more important from the sorts of things that you're going to need to be doing, is the idea of algorithms. So this is a definition of an algorithm, just a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. That's a dictionary definition. So I like to define it as a complete and precise set of steps that will solve a problem and achieve an identical result whenever given the same set of data to some defined level of accuracy. So key things are ordered steps, it's repeatable. The known and defined accuracy bit comes from the fact that you might be using random numbers as part of your algorithm, so you might be taking random steps, but you should, from that, be able to define some sort of expected accuracy. So let's look at a simple sort of algorithm and how we might go about designing an algorithm to do something very simple, which is to take this piece of protein structure, and we want to know how many amino acids are in this structure. So we would store this information in a PDB file. That's the standard format for data files containing protein structures. And we want to count the number of residues, number of amino acids. Now, the central atom in each amino acid, of course, is the alpha carbon. So here, 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 here. So we know that that's got to be present in every amino acid. So a good thing to do would be to count the alpha carbons. So here's our PDB file, standard format. First a keyword saying what the record is. This is an atom. Then we have an atom number, an atom name. So Ca represents C alpha. Amino acid name, a chain name. So you can have a structure file contain multiple copies of the same protein, or it could be a quaternary structure containing multiple chains that are interacting with one another. So this just gives you a label for the chain. This is an amino acid number, so we're just counting consecutively here. Then we have the XYZ coordinates, something called the occupancy, which is just when you have atoms that are flipping between different positions. Normally this is 1 when they're in one position. It might be 0.5 if an atom is spending half its time in each of two positions. And this is something called the temperature factor, which tells you how much the atom is vibrating. And then this is just the element type, so C or carbon, nitrogen, and oxygen mostly here. So what we're interested in is just how many occurrences of Ca there are in here. So here's a flowchart of an algorithm for doing that. So we start up the top, and we need some sort of counter to count how many residues there are. So we'll set that to 0. Then we have our PDB file, and we want to read the first line from that file. We want to see if we were at the end of the file. In other words, we've run out of lines of data. Obviously, we won't have to start with, so no. We see if the atom field was Ca. If it wasn't, we just go around here and we read another line. And we keep looping around this until we do find a Ca, in which case we increment the residue count. And we loop back then to here. Finally, when we get to the end of the file, we display the results and say how many Ca residues there were, lines there were. So this is a representation of an algorithm. Obviously, you can't take that and put it into a computer and get it to work. You need to write that in a programming language. And the language that you're going to learn some of on this course is called Python. Personally, I hate it, but which is why if you do BIOC3301, you'll be learning a bit of Perl, which is a language I like. But it has to be said, Python has become very popular in the kind of bioinformatics field. There are lots and lots of extensions and packages that do make it very good for exploring data and so on. That's really why it's taken off, not because of the language per se, but because of all the add-ons for it. So obviously this takes us from this idea of an algorithm, a set of steps, into the programming step. I've already mentioned Python, but there are actually a whole range of different programming languages. Of course, the computer itself doesn't understand any of those languages. The CPU, which is the chip that actually does the work, works in a thing called machine code. And this is a very low-level thing. There's something slightly less difficult to use called assembly language, but it's still horrifically complicated. And really nobody writes code in assembly language these days, other than a few little bits that operating system designers may have to write. People who write programming languages might have to write a little bit. Well, obviously their programming language has to generate it, so they have to know how it works. Occasionally, much less so these days, people like games programmers may do bits of assembly language because it allows you to get the optimum speed, because you're really just writing immediately for the processor. You're not having something else interpreting stuff for you. As I said, there are lots of these high-level languages, which is what we end up actually doing all our programming in. This is just a small selection of the languages. The ones that are, I would say, most popular in the kind of bioinformatics world are C, Perl, and Python. The next most popular being C++, Java, and to a slightly lesser extent Fortran, but that's very popular in the kind of computational physics and computational chemistry area, which kind of has some overlap in some cases. JavaScript is also very important. That's a somewhat different language in that it's used for implementing code within web pages. Then there are lots of other languages which are generally less popular these days. COBOL was really very important language to be a programmer in 1999, because a lot of business software is written in COBOL, and everybody was panicking that when the year 2000 happened and all these counters would go from 99 to 0, people would not be getting their pensions anymore because they weren't over 65 anymore, whatever it was. So there was a great demand for COBOL programmers for a year, but probably not anymore. But we can divide programming languages into different categories. So there are three kind of broad categories on the sort of 3 dimensions of this cube. So you could place each language into this cube somewhere. Along the bottom we have general purpose. So languages like Perl, Python, C are all general purpose languages. Through markup languages, which are things like HTML, which are used for creating web pages, through to specialized languages, maybe for doing statistics or querying databases or whatever. This direction we have interpreted through to compiled. I'll come back to what that means in just a minute, but it's basically going to tell you stuff about how fast a program runs and how easy it is to make changes and develop. And then the third axis there is about different programming paradigms, so ways of implementing your program. And I'm not going to go into the details of those. The one thing I will tell you is that Python, which is what you're going to be learning about, is general purpose. So it's here. It's part compiled, or just-in-time compiled. That's what JIT stands for, just-in-time. And it's object-oriented. So we're kind of at the back in the middle of this bit. So just a few examples of these sorts of things. Specialized, as I said, are things like, to some extent, JavaScript and PHP, which are used for websites. But in fact, they can be used for anything, but largely they're just used for websites. Things like R for statistics, SQL for querying databases, MATLAB and Octave are things for doing maths, heavy-duty maths type calculations. Markup languages, as I said, things like HTML for the web, TeX and LaTeX for producing documents. If you've got long things to write, like dissertations, I would highly recommend you learn LaTeX rather than trying to do it in Word. It makes your life so much easier. XML and SGML. XML is a data markup language. SGML, also data markup, not used so much these days. And then all these things that are general purpose. The language categories, whether it's compiled, interpreted, or somewhere in between, basically the idea is that when you write a program, you write it as a set of commands into a file, and we call that your source file. With an interpreted language, you have another program called an interpreter, which sits and talks to the actual processor, reads your source file, does what the source file tells it to do, calling the processor. It's taking data in and sending data out. That means that every time you run the program, the interpreter has to convert the commands into something that the processor can actually understand. The alternative is a compiled program where, again, you start with a source file, you run it through another program called a compiler, which talks to the processor, and that generates an executable program, which then can talk to the processor directly and process your data. So when you actually run the program here, every time you have to have this interpreter which converts your program and does it as you go. Whereas here, you've converted your program into something which can talk directly to the processor. So you don't need these bits anymore. You just need this bit and this bit. So that means that these programs will run a lot faster. It's also harder for other people to kind of hack into what you've done unless you make the source file available as well. The disadvantage is that every time you want to make a change, you have to go through this process of compiling the code again. So it kind of slows down the development, but the software runs faster. So here are a few examples. So things like Perl, a thing called Tickle, Bash, which you'll be using later, are interpreted. Things like C, C++, Fortran are compiled. Things like Java and Python are part compiled. So Java, you have to run your thing through a thing a bit like a compiler, but it converts it to a stage where then something else has to run. So it's sort of part compiled, part interpreted. Python will also sort of do that, but it does it completely automatically. So it appears like you're just running a normal interpreted language, but it will actually kind of cache a version which is part compiled for you. So it speeds it up a little bit. And in fact, a number of these things actually use what's known as a JIT, just-in-time compiler, which means that when they first start, they kind of compile themselves, and then they run that internally compiled version, rather than interpreting every line every time they see it. So if you're seeing the same line multiple times, you only convert it once rather than many times over. I'm not going to go into much detail about this, but procedural languages like C, Perl, and Fortran, basically you start at the beginning and you finish at the end. You might take steps off to something else on the way, but basically it's a kind of linear path. Declarative and functional languages, you don't specify how to do anything at all. You just say what you want back. So SQL, the database query language, you say something like select name from students where age greater than 30, or something like that. And you don't actually worry about how it does it internally. Prolog's an artificial intelligence language, R is a statistics language, XSLT is a language for transforming data files. Object-oriented languages, on the other hand, rather than being a program you start at the beginning and stop at the end, they have this concept of objects, which is a thing with data and methods or procedures associated with it. So you might have, I don't know, for a supermarket, you might have a product, and a product might be associated with its packaging, so it might be a can, it might have a price, it might have a weight, that sort of thing. And then you might also have methods associated with that, which are like apply a discount or whatever. So you sort of, it's just a somewhat different way of thinking about programming. So C is one that as a language I use a lot for things that need to run at fast speed. Perl's one that I use for more general purpose stuff. It's quite popular for web backends. It's been nicknamed the Swiss Army chainsaw of scripting languages, or the duct tape that holds the internet together. Has a very good library called BioPerl for handling biological data. So those are the two languages that I use, C and Perl. Python's the one that you're going to learn about. Design tries to emphasize code readability. It's quite concise. You don't have to write very much to do something quite powerful. It has a very comprehensive standard library of routines that comes with it for doing quite complicated things, plus specialized maths, scientific, and bio libraries, which allow you to do all sorts of useful things quite easily. So let's have a look at some fundamentals of programming which apply to most, well, pretty much all procedural and object-oriented languages, and that's the idea of variables. So we have different types of variables, three major ones, first of which is known as a scalar variable. And a scalar variable allows you to store one thing. So in this case, we've got a scalar variable, we've called it A, and we're setting A equal to 5. So it's a little bit like sort of concepts in maths where you have letters to represent numbers and so on. We can, or you can just think of it as slots where you can store a bit of information. So we've got something called A, and we're going to set it to 5. Now this is where maths kind of breaks down, because obviously from a mathematical point of view, A does not equal A plus 1. But the way that we use equals in a programming language is for assignment. So this means take the current value of A, add 1 to it, and set A to what the result is. So then here we're doing a print statement. We're saying print A. So if we executed those 3 steps, obviously it would print the answer of 6. So we set A to 5, added 1, and printed it. Scalar variables can also be used to store strings of text. So in this case, we're setting B to hello world. So if we did print B, then it would say hello world. The second type of variable is known in Python as a list. It can also be thought of, well, other languages call them arrays, but it can also be thought of as vector. So basically a group of numbers, or indeed a group of strings of text as well, that are associated together. So in Python we specify that with square brackets, and here we've said position, that's the name of our variable, equals 5.4, 2.7, 9.5. So we can print that whole list, but we can also print bits within it. So in programming languages, well, most programming languages anyway, we count from 0. So if I did print position 1, what's the answer I'm going to get? 2.7, yeah. So this is position 0, position 1, position 2. And here we're just overriding one of those settings. We're setting position 2 to 3.6 instead. The third type of variable is known in Python as a dictionary. In Perl it's known as a hash. It's basically the same as a list, but instead of using a number as an index, we use a string as an index. So the way that I tend to think of this is that if we go back to the lists, you can think of this as, so position in this case, the name of the list, as being the name of a road. If you have a road like Gower Street, you can then have a house number. And so you could get out whatever lives in that house. So you'd specify Gower Street to mean the whole road, or the whole list, and you'd specify a house number to access the person who lived at that house. A dictionary, or a hash, is one of those posh private roads that has house names instead of numbers. We have a road like that near where I live called the Warren. So you'd specify the house name in the Warren, and you could access the person who lives there. So this has certain advantages. Which, you don't have to search through. You don't have to know a number for something. You can just immediately access something very quickly just by its name, which can be extremely useful. So that's the first kind of basic computing concept. We have variables, which can be scalar, can be lists, or can be dictionaries. You've no idea how difficult it is for me to say that instead of saying arrays and hashes. I'm forcing myself to learn Python. We then have control statements. This is the second main concept, which is how you work your way around the code, whether you execute bits of code or you jump over them or you repeat them. So the first one of these is the if statement. So here we've got a bit of code that says x equals -6, and then we say if x is greater than 0, and then we have a colon. So after our control statement, we have a colon. And then we indent. This is Python syntax. We then indent and say what to do if that condition is met. And we can have lots of different statements in here. In this case, we've just got one. And they'd all be indented by the same amount. And then elif is short for else if. So in other words, if x is not greater than 0, but if it is actually 0, so we use two equal signs for a test. One is an assignment, two is a test. Print 0. Else, so neither of these conditions is true, print negative. So there are various test operators, which I just listed down here. Less than or equal to, greater than equal to, greater than, and not equal to. So obviously you could rearrange that bit of code in different ways to come up with the same result, but using different tests. The second type of control statement is a while loop. So here we're saying, first of all, x equals 5, and then while x is greater than 0, colon, because we're starting a block of stuff, and an indent, print x, and then set x to x minus 1. So what that's going to do is going to start off printing 5. It's going to reset x now to 4. It's going to loop back, test this. Yes, x is still greater than 0. So then going to print 3, loop round, print 2, print 1. And now when it comes back to here, x won't be greater than 0 anymore, so it will exit from this loop. Similar sort of thing is a for loop, which can be used in a number of different ways. It can be used for stepping through the items in a list. So if we've got a list here called x, we can just say for I in x, print I. So that will print 100, 200, 300 as it loops around. Just, it makes it much easier. You don't have to look at each item in turn and kind of look it up, give an index. So you don't have to say print x0, print x1, print x2. You can just loop through the items. We can also say for I in range 0 to 100. The range command is slightly odd. The first number is where you start. The second number, it's up to, but not including this number. So this will count from 0 up to 99, and then we'll print those numbers. And this third example, again, is like that first example, but this time we're using this range thing to count. So range 3 is that's a default there. So if we just said range 100, that gives 0 to 99. This gives us 0 to 2. Print xi. So that has exactly the same result as that, but here I is stepping through those indexes of 0, 1, 2, rather than stepping directly through the data that are in the array. So Mike will come back to all this stuff and cover it in more detail with you, I think. Well, some of it anyway. Okay, so that's basically the programming done, and we're now going to start to move on to our kind of command line workshop. But before we do that, I'm just going to kind of introduce a few little concepts that are important for that. First of which is the idea of folders, trees, and directories. Again, this seems to be something that to me seems like it should be fairly obvious, and I think most of you will find it pretty obvious, but some people again seem to get a little bit stuck with it. So this is happens to be a Linux desktop, but obviously it looks quite similar to a Mac desktop or a Windows desktop. And we have the idea here of some sort of file browser, explorer, whatever you want to call it, that allows you to browse through the different folders or directories, as we tend to call them in the Unix, Linux world, where you've got stuff stored. So here I've opened one of those. I've then clicked on BIOC3301, which was here, double-clicked that. It opened up another one. It's got a thing called lectures in it. I double click on that and it opens up this. So obviously you've got some sort of hierarchy there, and you can think of that as being like a tree. So here, don't ask why it says Reading. It's where I used to work, and I put all my work stuff under Reading. They have teaching, then different modules, then different directory, different folders, some are folders, some are actually data files or images within that, and then within lectures there's stuff within that. So you can think of it as a tree branching at each point. So this is somewhere where different operating systems vary somewhat in the way that they organise these sorts of things. So if you're used to using Windows, you're probably used to seeing things like C:\/ or D:\/ or Z:\/ or whatever. Each of those letters at the beginning is a root of a separate tree. And in general, they correspond to separate hard disks. In the Linux and Mac world, everything lives under a single tree. So everything starts at slash. And then we can have /home, /home/A Martin, which is my home directories, /data, /data/PDB. Now these top levels, like home and data, may or may not correspond to separate disks. Indeed, we could have /home and /data on one disk, /data/PDB on another disk. It's completely flexible, unlike Windows, where each disk is separate. In the Linux and Mac world, you can decide to put a new disk wherever you need it, basically, which gives you a lot more flexibility if you need to expand a computer system. Okay, so what we're going to do now is you're going to start to learn to use the command line. Mike, how do we get this going then?
All right, you need to log into the Bergfect desktop with the username UCL user and the password teaching spelled with a 3 and a 4 and a 1 instead of the E, A, and I.
So it's capital T, isn't it? Capital T, T34, CH1NG.
Do you have a marker somewhere?
I forgot to bring one, actually. I was going to. Capital T, everything else lowercase.
No, there's nothing around here. Okay.
No.
Right, capital T, 3, 4, CH, 1, and G. All right. And UCL loses all lowercase. And then you should get on the special desktop where you can then log in with the UCL username. No, the other way around. UCL user here. Ah, there we go. Everybody see that? Okay, once you're on the next screen, then you can log into UCL, desktop at UCL anywhere with your UCL username and your UCL password. And that should get you onto your normal classroom desktop. Once you're on the desktop, you want to launch a program called git bash, which you can just find by going into the task menu and typing git. there's like a git bash actually available on the BIOC thing as well, but
Oh.
no, but no. This is it, yeah. You can go full screen. Anybody have any issues? Yes.
Oh, yeah. All right, thank you. Just trying to know how to
Perfectly relaxed after 2.5 hours on the train.
3 hours and 20 minutes on the train. 2.5 hours away. Normally an hour. Yeah. 3 hours 20 minutes.
It's not good. It's just waiting on the train station.
No, waiting on the train.
Can you just command plus the thing bigger?
That's what I thought. It's doing that. Let's stop. Shut up. Just hit Control Alt Delete instead.
So now you're in the terminal, isn't it?
I just exited from there.
Does it log in out? Does it log out immediately?
Yeah.
Oh.
Well, under XXE it doesn't.
Okay guys, what we're going to do is you're going to type along with Andrew while he's doing stuff with the process. I'm going to go into your desktop, so desktop here. You can work on this one.
So it's not quite doing what I was hoping. I can't get a shell that I can make bigger. Okay, has everybody managed to get to a prompt? Right, so okay, so the first thing that you're going to do is just type in that command prompt, just type ls. Now let me explain why you're using something called git bag or git bash. Git bag has just heard something called it. Git bash. So Windows itself and the Mac and all computers basically have some sort of command line shell. Right. So Windows has one built in, and it's basically the same as the old DOS operating system that Windows kind of superseded in the early 1990s. Unix, or Unix type machines, so this includes Linux, actually have two main different command line prompt systems. One known as SH, which stands for shell, and the other one known as CSH, which is a little computing pun. It stands for seashell. And the syntax that you use is a little bit similar to the C programming language, which is why they called it a seashell. Now, the old original versions of these command lines were quite crude, and things like recalling a previous command you had to do in really quite obscure ways. And then, of course, people got used to the idea of just being able to use an up arrow, pressing the up arrow to recall a previous command. So people redeveloped the C shell into something called TCSH, which gives you these kind of nice extras. And the one that's just called SH became, which was actually short for the Bourne shell, B-O-U-R-N-E, like ultimatum. So this revised version became the Born Again shell, or Bash. So that's why it's Bash. Now, why is it Git? Well, Git is something you're going to learn about in a later session with me. Git is actually a system that we use for tracking changes that you make to code. So when you write a piece of software, or you write some scripts for automating something, you're generally going to be making changes, and you're going to want to track the changes that you make, and maybe where you ended up with errors creeping in, or that you added a new feature to your program or whatever. So Git is actually a system that is designed for tracking these changes, and actually allows you to synchronize everything with a central server called GitHub, which you can access over the web. And it's a way of allowing you to share your code with other people, but also gives you a kind of cloud backup of the code that you've written. So Git Bash is a thing that was written for Git to allow you to use the Born Again shell on Windows machines. So basically it kind of draws together the different sort of communities. And because you're going to be using Linux machines later for doing analysis, this is just a good way of teaching you how to use the Bash shell. Git, incidentally, why is it called Git? Well, it's actually something written by the person who designed Linux. And he's not very specific about why it's called Git, other than that he's a bit of a git. So he decided to name it after himself, because the operating system Linux, his name is Linus Torvalds. So he took the name Linus and added the X bit from Unix. I'm sorry I can't get this to look any bigger. I hope everybody can see it. Basically, when you typed ls, you should have got something like this, which is just a listing of all the files and folders that are in your home directory. You get anything like that?
What type of
ls.
Oh, sorry. Oh, yeah.
Right, yeah. Okay. So you should find that some things are highlighted in blue and have a slash on the end of them. Some things may be in other colours. The important thing at this stage is that the ones which are highlighted in blue and have a slash on the end are themselves subfolders or directories. They're in the kind of tree thing that we were looking at. This means this is a directory within this current directory. Anybody who's confused by that idea of trees and directories? I have no doubt that somebody will be confused when we do the next bit today. Right. So you know that when you're using a point-and-click interface, you can create a new folder, a new directory, by usually right-clicking and then choosing new folder, something like that. So how do we do that here? Right, what we're going to do then is create ourselves a folder called BIOC3301 to experiment in. Okay? So I'm just going to do something confusing and go somewhere else to do this. So ignore that first command that I gave. But this is the command you want. mkdir, which stands for make directory. So I should say that ls, which is the command you used just now, stands for list. It's just listing what's in the current directory. So we're going to do mkdir space BIOC3301. And if you press return, then the command prompt should simply come back to you. And you'll see nothing else. But if you do ls again, you should now find that among the directories that you've got, folders that you've got, you should have a new one called BIOC3301. Everybody managed to do that okay? Right, let's do something slightly different before we actually make use of that directory. If you type the command pwd, and that should come back saying something like, what does it say for yours? C or /c/users/ whatever. So that's telling you where you currently are. PWD is print working directory. So it's telling you which directory you're actually in. Now if we try ls minus L, we again will get our list of things that are in the current directory, but this time the minus L stands for long format. There's ls space minus L. So this tells you some information which I won't explain yet at the beginning. Ignore the number. The next line should all be your username, because it's saying that the files belong to you. And then there'll be a group name, so every file is assigned to a user and a group of users. Just out of interest, what's the group called on here? It's just a number, okay. So you just have a numeric group. You'll then have another number, which is the size of the file, the date, the time at which it was created, and then your information about the actual names of the files. You can also do a few other little things around this. So you can do ls minus L, that was the long, and T. So minus LT. That will give you exactly the same information that you got before, but this time the T stands for time, and it will sort the files by time. So you've got the newest ones at the beginning, the oldest ones at the end. Generally, it's more useful to have the newest ones at the end of the list, particularly if you've got a lot of files. You see what you've just created. So if we put an R on the end of that as well, ls minus LTR. So ls for list, L for long, T for time, and R for reversed. So now you'll get the latest file or latest directory at the end of the list and the oldest one at the beginning of the list. Okay? So what you should see when you've done that ls minus LTR is that your BIOC3301 folder that you just created is appearing as the last thing in the list. So now we're going to change to that folder and make use of that folder. So just as with a point and click interface, you might double click on a folder to change to using that folder. We're going to do the same thing from the command line. Remember, we call things directories in Unix instead of folders. So we want to change directory. So what do you think the abbreviation might be for change directory? CD. Okay, so CD BIOC3301. Now, before you type that, do the CD and type bio, and now press the tab key. And you should find, if you've got nothing else in your sort of home directory, starting with bio, the line should complete to say BIOC3301. That work here? Yeah. If you did have something else starting with bio, it won't have completed BIOC3301. But if you press tab again, then it will list all the things that start with bio, and you can just add another character, like the C, and eventually you'll have added enough, keep doing that, you'll add enough characters, it becomes unique. This can be incredibly time consuming. If you've got long file names, you don't have to type them, you just press tab. So type CD BIOC3301, and how we're going to find out what's in that directory. Type, well, PWD will tell us that what directory we're in, which is now the BIOC3301 directory, and to see what files are in there, we do an ls, and we should get nothing back because we've just created that directory. Right. Just see if there's anything else that I wanted to. Okay, so we could carry on doing this, making subdirectories, making a whole tree of directories like this. Use CD to navigate them, PWD to remind us which directory we're in. How do you think we get up again, though? Because we're going down our tree at the moment, so out towards, well, up our tree towards the branches. We usually think of trees upside down. If instead of just doing ls, we do ls minus A for all, you'll see you've now got two folders, so two directories within that directory. One of them is just called dot, and one of them is called dot dot. The one called dot kind of means nothing really. It is this folder. This folder is called dot. So if you did cd dot and we did pwd, you're still in the same place. There is a reason why that's useful, which we'll come to later. The dot dot represents the folder above. So if we want to go back up a folder, I can do cd dot dot, now do pwd, and you'll find you're back in the folder above. Right, so go back down into your BIOC3301 folder. So cd bio tab. Now there's another way of getting straight back to your home folder. So when you first opened up Git Bash, you were in your home directory, your main directory where you store stuff. And since you quite often want to get back there, you can do that very quickly just by typing cd on its own. change directory by itself will always take you back to your home directory. So mine's called local home, local user. Yours will be called C, whatever it was, /C/ something like that. I'm going to go back to where we were. Right, has everybody kept up? Does anybody need some help? Need to? There are lots of people wandering around, so do just put your hand up if you're not kind of completely clear with what we've done so far. Okay, everybody happy? Right. Okay, so what? I've just got my list of things that I wanted to cover here. Okay. So the next thing we're going to do is look at how do we look at a file. So wondering how this is going to work on these. Let's get a file to look at first. Now, can I just try something on yours just to make sure that it works under Git Bash? Okay, so we're going to use a command to grab a file from another machine. So we could do this using a web browser. Okay, so if you open a web browser, and go to the URL www. I don't know if anybody can see it over here.
Well, I guess you could write it on the keyboard on the screen.
That's a good point, yes. Why don't I do that? That's a very good idea. Let's just... Okay, so URL is www.bioinf.org.uk/teaching/BIOC3301. Everything in lowercase. Right, annoyingly, I can't persuade my laptop to connect to the likes of Edurome. It's being a pain. But you should see on there that there is a link for download example files. Just hover over that. Right. So you can do that, but I'm going to show you how to do it from the command line instead. So rather than download this from the web, now you can do that. You can click on it, you can save it, and then we can look at it from our command line. But instead, what we're going to do is type curl http://www.bioinf.org.uk /teaching/BIOC3301/pdbs.tgz. Now, make sure you've CD'd into your BIOC3301 directory first. So curl http://www.bioinf.org.uk/teaching/BIOC3301/pdbs.tgz.
Did you have to dash O, hyphen O to download?
I don't know, I never use curl, normally use
I think
wget.
it's hyphen O to download, otherwise you get the HTTP header.
Okay.
Slight correction to that command.
No, I typed it.
I think it's a capital O or something like this. Hyphen capital O, if I remember it correctly.
Slightly annoying, I can't actually do it because I can't get the Edgerome to work. It's working in the office, it isn't working here.
There it was, wasn't it? Cool. You're getting there. Let's just try it out. If it works with the O. Yes. Dash O.
Okay, so
Is that O or 0?
It's an O. Alright.
so curl minus capital O HTTP.
Yeah. So you could just push your up arrow key on your keyboard to get that command back on the screen, and then use your left arrow key to scroll in between the curl and the URL and add the minus O in there.
So curl is essentially a web browser from the command line, if you like. So instead of you opening, Firefox or Opera or Chrome or Internet Explorer, if you really must, instead it allows you to grab a page of information from the web without bothering with a web browser. There's another program called wget which does the same sort of thing, and that's the one I'm used to using, which is why I didn't know about the -O thing. Yeah.
Mine is completely messed up.
That's probably because you didn't have the -O.
I did.
Oh, you did?
Yeah.
In that case,
It has to be an O, not a 0.
no, I don't think you have that.
Uppercase O. Right? Uppercase O. I don't remember what that was.
Okay.
I want to show them how to copy to the right place in case they put it into the wrong place.
Okay. So is it lowercase o or capital O? Capital. Because for some people it's just appearing on the screen.
The type is 0, I think.
Did you use a 0 instead of an O?
No, I used capital O.
You should, because the O and the
Yeah.
0 is very close to each other on the keyboard as well. Oh yeah, it's fine, you downloaded it.
I've done it,
Yeah.
yeah. But,
Oh,
okay, so if for any of you, so this is actually a very useful thing to learn anyway. If for any of you it's not downloading when you type that, maybe because you've inadvertently done a 0 instead of an O, or maybe because of something else. So you're just getting a load of weird stuff appearing on the screen when you type that. What you can do to get around that is just add a greater than sign and pdbs.tgz on the end. Now, we'll come back to this greater than sign and what it means in a few minutes, but basically it means send the output of this command to a file. So because the output was appearing on the screen for some people, instead of going into a file automatically, this will force it to go into a file.
Although it might be that what is appearing on the screen is the HTTP header of that file from your server.
That should only be 2 lines though. So it shouldn't be. But yeah.
We shall see now.
So, if everybody types ls, if they've managed to achieve this properly, and this is not going to work for me, so I'm going to just have to copy it over instead. Okay, so hopefully, if you've done this right, you should have a file in your directory, and it should be the only file in the directory, and it should be called pdbs.tgz. If anybody has forgotten to go into their BIOC3301 folder first, then obviously you'll have lots of other files appearing as well. In which case, you would want to move it into the right directory. And remembering the way that Unix, Linux likes to abbreviate everything, the command for move is mv. So you just type mv pdbs.tgz space BIOC3301, and that would move the file into that directory. So the move command is used both for moving files from one place to another and for renaming them. So we could, if we wanted to rename that to files.tgz, you type mv pdbs.tgz to files.tgz. Now if we do an ls, it's now called files.tgz. Okay? So I'm just going to move it back again. So has everybody got that file in their BIOC3301 directory? Right. So that file is a bit like a zip file. It's another format that we use in the Unix, Linux world quite a lot, called a gzipped tar file instead. So tar actually stands for tape archive. It was originally a program for archiving directories and stuff onto those tapes that we looked at earlier. But these days it's still used for that because people do still use kind of cartridge tapes. These days it's mostly used for just packaging a whole set of files together. That's what we've done here. And then it's gzipped, which is a compression thing. So the tar bit doesn't do any compressing. The gzipping does. So we want to uncompress this and extract the files from it. So we type tar, X for extract, V for verbose, Z to say it's a gzipped tar file that we're wanting to pack that's been compressed, then F, and then the name of our file. So tar, tape archiver, X, extract, V, verbose, Z, it's compressed, and F, which means you're not going to get it off a tape, you're going to get it from a file. And then the name of the file. And press return. And if everything has worked properly, it should list 6 files. Does that work for everybody? Excellent. Glad it's worked for you. Right, it hasn't worked for everybody. Okay, one more time. Okay, anybody else not managed to get that to work? Okay. So what you have now got, if you do an ls, you should find you've now got your gzip tar file, the thing that we downloaded, and you've also got now another folder within your BIOC3301 folder. You've now got a subfolder called PDBs. So change to that folder. What command do you have? You should remember which command you need to type to change that folder. CD PDBs. And if we do an ls in there, should find that you've got these 6 PDB files, protein structures, that were all packaged up for you in that gzip tar file. It listed the names of them when you unpacked them because you put the V in the unpacking command, and here they all are. Right, so what we're going to do with these. Yeah, the first thing we want to do is actually look at the content of one of these files. So let's choose the first one, which is pdb9aat.ent. And to display it on the screen, you type cat. Very obvious. There is a good reason why it's called cat. Nothing to do with the fact that I have 5 cats. If you do that, one of the files, press return, you should get the file zooming past you on the screen. Now, the reason that it's called cat is actually because it's short for concatenate. So, if I wanted to take all 6 of those files, well actually, let's just do 2 first. So do ls again and do cat pdb9aat pdb9abp. If I do that, then it will display one of the files, then it will display the other ones. Okay, obviously it goes past so fast that you can't really see very much information. So it's concatenating in the sense that it's taking each of the files that you specify and displaying them on the screen as if it was one file. Remember what I said to the people who had the problems with the downloading, that you can send the output of a command into another file. So I could use a greater than and then make up a name like, say, both.pdb and press return, and that would actually concatenate those 2 files together and put them into both.pdb. So if we do an ls minus L, you can see the first one we took was 610578 bytes. If I put if I do ls minus LH, H for human, it'll tell us in kind of kilobytes and megabytes and things instead of just numbers. So that first one that we used was 597 kilobytes. Second one's 238. Add the two together, and you get about 834, which is what the both one was. Everybody happy with that?
No, mine's not working anymore. When I edit it, it's not.
I think I might have accidentally set up a control S, which freezes the screen. That's the only thing I can think of.
What's the H file?
Human.
Human readable files.
So it gives you the numbers in kilobytes and megabytes rather than just in bytes. Okay, so cat displays a whole screen. We created this both.pdb, but we don't really want that now, so we need to know how to remove it. So, given that I said remove rather than delete, what do you think the abbreviation might be in Unix world? RM. Good guess. So RM both.pdb.
Logically, it would be RMP.
Well, remove. It's two syllables, so one for each syllable, I suppose. And it may, depending how Git bash is set up, it may prompt you to say, do you really want to delete this? Suppose we had a large batch of files, as we have here, and we wanted to concatenate all of them into one file. It would be a bit of a hassle having to say cat pdb9aat, pdb9abp, etc., etc. If we want to concatenate all the .ent files, we could just say cat star.ent into all.pdb, for example. So star matches any characters. And again, if we do the ls minus lh, you can see now that our all.pdb is 1.7 megabytes, so it's all of these added together. I don't actually have a good example there, but you could have done something like PDB 9 star. This is obviously going to match all of these, but you know, if you had PDB 8s and PDB 7s and PDB 6s in there, this would be a selective way of doing it. So basically, star just matches any characters, any number of characters as well, between two places. So you could even do something like P star 9 star, and that would match P followed by any number of characters, followed by 9, followed by any other characters, followed by .ent, and so on. Okay, so I'm going to remove my all.pdb again, which is just a demonstration of how you can concatenate things. Okay, so you've learnt how to display a file and how to use that same command for concatenating things. But, as I said, cat's not particularly useful for looking at files unless they're very small files, because everything just zooms past you. So there is another command which makes it much easier to do that, which is called more. Now, I don't actually recommend that you use more, because there's a better version of more, which is called less. Don't ask. Computer scientists have strange senses of humour. So what more does is it allows you to display one screen's worth of information at a time, and you press the space bar to go on to the next screen. You can also search within the file to find particular things. The problem with more is that you can only go one direction through the file. You start at the beginning and you gradually page through to the end. You can't go backwards at all. Less, as the name sort of suggests, lets you go in both directions. So let's use less to look at pdb9aat.end. And so what you should find is that you've got a screen full of information. Doesn't matter which one you look at, just one of the PDB files. You have a screen full of information there, which is telling you various information about this particular protein structure. And if you press the space bar, it should go down a page. And you can carry on going down a page at a time pressing spacebar. If you press B for back, you go back up a page at a time. Okay, if you want to get straight to the very end of the file, you can do a greater than sign. So Shift greater than will take you to the end. And can you guess what will take you to the beginning? Shift less than. So this allows you to page through the file. Suppose we wanted to look for a line that has the word atom in it. If you do a slash, and it's case sensitive, and this needs uppercase, so ATOM /atom, it will take you to lines that have /atom, have the word atom in them. And if we just do a slash by itself, it'll carry on doing the same search, and it'll take you in turn to each line that has atom. And eventually you'll get to the set of lines that start with word atom, which are the actual coordinates of your, the XYZ coordinates of the atoms in this protein. Okay, so less is very useful for getting through, moving around your file. And when you want to exit from less, you just do Q for quit. Okay, so we've discovered how to create directories, how to move around directories, or change directory. We've also kind of accidentally discovered how to move a file with MV, or rename a file. The other thing we might want to do rather than renaming it is copy it. Now you could use cat for doing that, because we could say cat. So if, let's just do a quick ls. I could say cat pdb9aat into copy.pdb. So that would do it. If we have a look with sizes, you can see that copy.pdb is exactly the same size as that 9AAT. We could prove that it's exactly the same using the command diff. So diff looks for differences. So if I said diff pdb9aat copy.pdb, I'm hoping that there are no differences between these two files. So when I run this, nothing comes back because there are no differences. Okay, we'll have another look at well, let's do it now. Another command that's quite useful is called head. Head just takes a specified number of lines from the top of a file. So let's just have a look at one of these files. Let's take the first, I don't know, let's say 20 lines of this file. Suppose we want those 20 lines. We could say head minus 20 pdb9aat, and we'll send, if we just do that by itself, we'll just see the first 20 lines. Can you guess what the command is for finding the last 20 lines? Think cats again, not humans. Tail. That's it. So tail minus 20 would give you the last 20 lines. So if we wanted to keep the first 20 lines, we could send that into, let's say, pdb9aat dot top or something. Should point out that this is something that's a bit different from Windows. In Windows, the file extension, the bit that comes after the dot, is always meaningful. So, you know, Word files are .doc or .docx, and they're meaningful because those extensions are associated with a program that's used for viewing that file. So if you renamed a file from, I don't know, thesis.doc to thesis.xyz, and you tried to click on it, Windows wouldn't know what to do with it. From a command line like this, you can use whatever extension you like for things. So .ent is the standard extension used by the Protein Data Bank for entries in the Protein Data Bank. It stands for entry. Most people, when they're dealing with PDB files locally, you know, they've extracted something, they've renamed it, they've copied it or whatever, they use .pdb as their extension. So here I'm using .top because it's the top 20 lines. So I've done that with one of them. Let's take another one. So I've taken the first 20 lines from 9AAT and the first 20 lines from 9ABP. Okay, everybody managed to do that? So it's head minus 20, the file name, send it to some other file name. I'm using the same stem, the 9ABP, and then top. It doesn't matter, you can call it whatever you like. So once you've got those two files, and I can do ls star.top just to list my two top files rather than my my ent files as well. And then I can do a difference between star.top and that will show me how those two files differ from one another. Remember when I did the copy and the original file, they're identical. Here we're seeing what the differences are. So again, that all scrolled past a little bit quickly, Now, how do we look at things gradually before we use the less command? Now, Unix gives you another kind of concept, which is called pipes. Now, just as we sent the output of this command into sent the output of the head command into a file using the greater than, I could say diff star.top into differences. Differences.txt, for example. And then I could use it less to look at differences.txt and scroll through them and see exactly what the differences were. But that's a bit cumbersome, having to put stuff into a file and then look at it. So this is where this concept of pipes comes in, which is that we can, instead of sending it to a file, if we use the pipe symbol, which is the vertical bar, probably bottom left on your keyboard, we can actually send the output, instead of it going to the screen, which is the default, or going to a file, which we do with a greater than, we can send it to another command, like less. So less, rather than taking its input from a file, takes its input from what came out of that program. So now we can very quickly look at the differences between two things and move around, see what's going on.
The pipe key is next to the left shift button. Yes.
Should we take a 5-minute break? Think? Want a 5-minute break? We've got a few other things to look at. So just break for until, well, let's say 20 past, and then we'll look at a few other ideas.
Right. Let's pause that.
Mike has just said to me it's worth pointing out that there is no undo, there is no wastebasket or anything like that. So if you do an RM to remove something, you have lost it. Unless, I mean, most people with running any sort of decent sort of size computer system will have some sort of backups going, probably daily backups, running automatically every night. So at home, I actually have another cheap computer that I built for sort of 120 quid or something, sitting in the shed at the bottom of my garden, and actually have electricity down there and an Ethernet cable running down to the bottom of the garden. And every night, my computer backs itself up to a disk on the machine down there. So even if the house burns down, I don't lose stuff. But and for my computers in the lab at work, we back stuff up every night to a big big NAS box. So it has 24 terabytes of disk space on it. We do a backup every night. So if somebody does delete something automatically, accidentally, the worst they're going to lose is sort of 24 hours worth of stuff. They can recover it if they haven't, if it's been done in the last day or so. So having said that, though, there is a flag that you can give to RM, which gets it to prompt you whether you really want to do this, whether you want to delete things. So if I So I got my copy.pdb. If I did rm minus I copy.pdb, it would say, do you really want to remove this, basically? And then you can press Y for yes, or N for no. So using that, I could do something like rm minus I star dot top, and then just say yes to the ones I want to delete and no to the ones I don't. And if you are the sort of person who does delete things by mistake, you can actually set up what's called an alias, so that copy is always cp minus I. So you can just say alias cp equals single inverted comma cp minus I single inverted comma. Sorry, I didn't mean cp, did I? I meant rm. So I've done alias rm equals rm minus I. So if I now do rm differences.txt, then it does that prompt. Obviously that would be a bit of a hassle if you had to remember to do that alias every time you wanted to do it. Every time you wanted to open a shell, you had to do that alias again. So you can create a file in your home directory. So if you do cd, take you back to your home directory. And in there we can create a file. And I don't know for these systems exactly what it'd be called. It seems to vary between different systems, but it's probably called .bashrc. So that's .bashrc. It might also be called .profile. So you can create a file in that directory called .bashrc or .profile. So I'm not sure which it is. And you can put your alias command in there. And then whenever you start up your git bash, it will automatically run the commands that are in that file. So your alias, which means that everything is set up as you want it. Right, there are various ways of creating files, and when you start to do the programming stuff with Mike, you'll find out about proper text editors for doing that. We're not going to look at that now, but there is one way that you can do it very kind of quickly if it's a single, very simple thing that you want to do. So, just going to go back into my BIOC3301 directory. So if you need to get back to here because you've moved somewhere else, just type cd and then cd BIOC3301. Or you can actually combine that because the tilde, the kind of wavy line, is an abbreviation for your home directory. So if I had gone into, let's go into CD PDBs, and I want to go straight back to BIOC3301. So if I do CD space tilde slash BIOC3301, that will tilde is my home directory, and then BIOC3301 is the subdirectory of that. So I can just do that as a very quick way of navigating around. Oops. Yeah. So I just clicked the wrong thing and closed everything down. Okay, so you can actually, you might have spotted, I'm using an alias there. Because you want to do ls minus l so often, I actually have an alias of ll, alias to ls minus l. Just saves me a bit of typing. Okay, so I'm going to show you this very simple way of creating a file. which is quite useful if it's just 1 or 2 lines that you want to create. And that is to use the cat command. So cat, like ls, and like most of the kind of Unix commands, if you don't tell it otherwise, then it will expect to read from the keyboard and write to the screen. Okay? So when we used cat before, we said cat and then a file name, and it appeared on the screen. Or we did cat, file name, redirect with a greater than sign, and it sent it to a file. So if I just type cat by itself, and try this, and press return, it just sits there and does nothing. That's because it's now expecting its input from the keyboard rather than from a file, because you didn't tell it to read from a file. So let's type hello and press return. And it echoes the hello back to the screen again. Because remember, it's taking input from the keyboard and output's going to the screen. So I can type anything I like and it will just keep echoing it. And that will carry on until the file ends. Well, there's no file, it's the keyboard, but we can tell it it's the end of the file by pressing Control, holding that down and pressing D. Okay, so how could we use that to create a file? Well, we just redirect the output into, say, test.dat. So I just type cat greater than test.dat, press return, and it waits for me to type something. So I shall type, this is a test, and press my Control D. Now if I do an ls, I've now got a file called test.dat, and I can display that on the screen with a cat, and it's got the content that I just entered. So it's quite a useful thing, just, you know, if you just wanted to write 1 or 2 lines and you're not going to make any mistakes, because you can't, obviously you can't edit it as you're going along except on that current line. So if we wanted to create this .bashrc file, normally you do that in your home directory. I'm not going to do it in my home directory, because if I did, I would mess up my .bashrc file. But I could do cat into .bashrc. I could say alias rm equals rm minus I. And I could do alias ll equals ls minus l. Oops. And Control D. And then I've got my bashrc file that would have those aliases in. So then in future, when I run git bash, it will have those commands in it. Okay? Another useful thing, actually, because I don't know if these systems need it to be called .bashrc or .profile, it'd be quite useful if I had both file names. Now, it would be a bit silly. I mean, I could just copy this file, having edited it. I could copy it with CP. So that's, I don't think I actually ever told you that. That's the other way of copying files. Obviously, I could do it with cat from this file name, redirect to the other file name. But you can also just do CP, copy. So I could type copy.bashrc.profile. Profile. But that's not going to be a very efficient way of doing things, because if I decide to add an extra alias or some other command into my .bashrc file, then I'd have to also add it to my .profile file, which is obviously not very sensible. Now with Windows, you should be familiar with the idea of shortcuts, and there's similar sort of thing on the Mac as well, and the way that it works in Unix, Linux, and of course the underlying way it works on the Mac is with what's called a symbolic link. So instead of doing the copy, we can just do ln, which means link, minus s for symbolic, dot bash rc dot profile. And what that means is basically just that either the name .profile or the name .bashrc will allow me to access the file.
Mine's been failed.
Yours?
Same.
Oh, dear. Okay, that's because you've already got something called .profile. So presumably, just have a
Shall I
quick
remove
look.
it?
Not. That's because you've already done copy to make it. Yeah, you did copy of that. So you've already got
Should I
it.
just...
So I said this is what you could do. So I'll remove it.
Do I?
And just do it.
I already have something that's called the profile apparently.
Okay, so for if for anybody this has failed,
Are you
this
doing a link?
ln minus s dot bash rc dot profile has failed, and it said dot profile already exists. It's because you did the copy dot bash rc to dot profile, which I said you could do, but is not the best thing to do. So in that case, you want to remove your dot profile.
Can remove that.
So rm space dot profile,
Just type rn.
and then do the ln minus s dot bash rc dot profile.
Okay. No.
Don't worry, if you're interested why it needs the minus s, I can tell you, but basically don't worry about it.
Yeah.
Just ask me if you want to know.
Okay.
Ooh.
Whoa.
Okay. Now you can use Symlink again.
Okay, so because you don't want to have to log out of git bash and then log in again, just type
In the
source
wrong.
I don't know.
dot
in the
bash
wrong folder
rc,
anyway.
I thought I was already in.
and that will then just run all the commands that are in that file.
Did you add your aliases already? Oh, you did add your
Oh, I did
aliases,
one
yeah.
of those.
Alright. So, you know the source. As Andrew just typed.
So as you can see, nothing has changed on the screen, but if I type alias, LL, then it tells me that now LL is an alias for LS minus L.
There you go.
And if I type alias RM, it tells me that RM is an alias for RM minus I. So now when you try and delete a file, it'll give you that, that prompt.
Right, so whenever it gives you like the command prompt or something.
Now, you may also have noticed, if you do an ls in this directory where you've just created your home directory, where you've just created your .bashrc and your .profile, ls, or if you do ls minus ltr, so that you get the most recently created file coming up last.
What if they have typos in their bashrc file?
Delete it and start again, because I'm not going to tell them how to use an editor.
Okay.
if your RM command isn't working because of the alias with a backslash in front of it. Yeah, it's not working.
Sometimes if I tap the wrong thing, you just have to do it again.
Yeah, I know.
This is not my favourite.
Okay, so what you should have found in your top directory, even though you've created these two files, if you do my ls minus ltr, they're not appearing. And that's because they start with a dot. Any file name that starts with a dot, by default, is not shown. So it's like in Windows, you can have hidden files. This is how we hide files in Unix. So if we do ls minus ltra, remember we did ls minus a before when we found we got the directories dot and dot dot? Mm-hmm. This shows everything. So it's a for all. And you should now find that you've got your .bashrc file, and you've got also .profile with a little arrow to .bashrc. And that's telling you that .profile is a link or shortcut to the .bashrc file.
Yeah. Oh.
Okay, so things that we've covered so far, basically we've done listing of directories, we've done how to create a directory, we've done how to look at files and concatenate files. We've used that concatenating command in order to create a file. We've created symbolic links or shortcuts. We've moved files around, renamed them, moved them. Just a couple of other things we want to do. So one of those is, although I've shown you how to create files and remove files, and I've shown you how to create directories, but I haven't shown you how to remove directories. So let's just make another directory. We'll call it foo, F-O-O. Just to explain another bit of kind of computing folklore for you, people often refer to kind of random stuff as foo and bar. And this comes from the American Army term, FUBAR, F-U-B-A-R, which stands for effed up beyond all recognition. We often just use foo and bar as kind of random names for things. So I'm going to create a directory called foo with mkdir. So I've now got my directory foo, and we can't remove it using rm because that's for files. So if I try doing rm foo, it will say can't remove it, it's a directory. So instead we use rmdir, like mkdir for making directories. We use rmdir to remove directory. Now I'm in my BIOC3301 directory, which has got my PDBS thing in it. If I try removing that, it won't remove it because it's not empty. So rmdir can only be used to remove empty directories. If I want to remove a directory and all its contents, then I can do rm minus rf, and the r here means recursive, so it steps down through anything that's below this, and f means false. Don't ask any questions, just do it, which is generally not a good thing to do, but if you are absolutely sure that that's what you want to do, you can do rm minus rf PDBs. And I am going to do that, and you can see it's gone. I'm now going to recreate it by re-extracting using the tar command. So I've got it back again. Right, so let me just remind myself what we're going to cover. Right. Those are all basic things, manipulating files, etc., etc. I'm going to show you now how you can really do something quite clever with this sort of thing. So let's go into your PDBs directory. And do you remember the example that I gave you in the sort of lecture bit at the beginning about programming? And the example for an algorithm was how to count how many amino acids were in a PDB file. We don't need to write a program to do that if we understand how to use Unix and Linux, because we can do it all on the command line, just with basic built-in commands. So, one of the most useful commands is slightly strangely named command called grep. The grep really means search. It stands for Global Regular Expression something, pattern, something like that. So suppose we wanted to take our PDB file, let's take this first one, 9AAT, and we wanted to pull out just the atom records. If you remember, if we have a look at this, each record in a PDB file starts with a field at the beginning which says what this line contains. So, for example, we have a header, we have a title, we have compound, source, keywords, etc., etc. And if we go down far enough, beyond all these remarks, we have atom records, which are our actual coordinates. Okay? So we can do grep atom on that file, and we'll just get the lines that have the word atom in them. Let's just pipe that into less, so we can see if we're only getting the lines of interest. Well, no, we're not. We're getting other ones that had the word atom in as well. Right? So not just the ones that started with atom. If we do... I think this works. Yeah, so if we put before the atom an upward hat, circumflex, caret, whatever you want to call it, doesn't need to stick the quotes, that forces the match to be at the beginning of the line. Okay, so this then grep hat atom pdb9aat dot ent piped into less means I will just get the lines that start with the word atom. Okay, so that's allowed me to extract from the PDB file just the coordinate records. Now, obviously sending it into less isn't that useful. What we want to know is how many lines there are. That will tell us the total number of atoms in the file. So there is another useful utility which can count words, characters, and lines. Now, if we can count the number of lines, that will be the total number of atoms in the file. So, given that this program, its general name is word count, what do you think the slightly unfortunate abbreviation is? WC. Right, so if I pipe this into WC instead of, sorry, I sent it down the toilet, instead of into less, I get three numbers out, First number is the number of lines. Next one's number of words, so space delimited fields, and the next one is the number of characters. So I know from that that I've got 6,322 atoms in total in that file. Now, suppose I wanted to count the number of amino acids, and we were going to do that by counting the CAs, the C alphas. I could do that by taking, so if I just do that, I've got the atoms, and I could now send that into grep.
No, it's working. If you want to quit it from working, you can always do it.
So I'll wrap it in a couple of spaces. So I put single inverted comma space CA space single inverted comma, just to make sure it's a CA by itself, not part of something else.
Right. It's a PD. That's why you should autocomplete.
And if I run that, so that's grep hat atom file name piped into grep single inverted comma space CA space single inverted comma. From getting that, from running that, I would just get all the CAs from my file. So then if I pipe that into WC, I find that I've got 802 amino acids in that protein. Now try doing that from a Windows graphical interface. You just couldn't. And, it just becomes automatic. If I wanted to do it instead across all these PDB files, and I want to know how many amino acids are in all the PDB files, well, I could just rewrite this slightly as cat, the file name, into the grep for the atom, into the grep for the C alpha, into the WC. That should give me exactly the same answer I got before, which it does. But if I wanted to do it across all the files, I could just say star.ent. So across those 6 PDB files, I've got 2,117 amino acids. So this pipe concept is remarkably powerful. You can do all sorts of things to process whole sets of files, do all sorts of manipulations on them.
So the word count is giving you words, characters, and...
So this is number of lines, number of words, number of characters. So if I only wanted the number of lines, which is actually what I'm interested in, I could add -L on the end. Is everybody keeping up? Anybody need some assistance? Before I just show you one last thing.
I think this is to remove the iron. You just want to know how many
Less.
keeping out. I don't know, like,
Not quite sure what you're doing.
but how they can undo things. I thought like if you type the second one right, that you can do right. Apparently just now I typed something longer and didn't realize. Then we type it and I was thinking, okay, it will work. But if then you have to remove it yourself. Yeah. Because I think I went to Exeter to visit my sister-in-law.
Oh, okay.
My sister was was working there, but then now she moved to a different place already.
Where's she now?
Norwich.
She's not.
I've never been there yet.
So Norfolk.
Not really.
It's still
Quite close to London actually. I would say it's actually closer than Exeter.
it's like an hour. Are you like sharing?
Yeah, like she just in the train and
It's not too bad.
because Exeter is 5 minutes.
Yeah, X.
Exeter, I took like a bus that takes like 5 hours.
You can always do, if you're really curious,
4 hours
you can
plus,
do
because I was like after working hours and it was like paid. And the train ticket was super expensive, so I took bus and it's like not too bad. But then so I think I really reached her place around like 10 o'clock at night. It's just that the bus is very inconvenient though, like how they actually have like during night time it's just an hour. Like no, I got like, it's not frequent at all, either always like an hour. Yeah, because she's not living very Exeter.
Oh, she's not actually.
Yeah, so you have to reach Exeter bus station and you take a bus. It's like about I think 45 minutes from the bus station to her place. So her place is somewhere in between. It's like close to the seaside, so it's weird.
Yeah, it's really nice.
But then the transport is gonna be a problem, especially if you're reaching after.
You need car. So it's easier for you.
Yeah, if you're driving then. Yeah. It doesn't say much time, like driving also takes about like 30 minutes. Yeah, so it's
It's okay, it's okay.
yeah, but it's just that when you miss the bus station, it's gonna be really bad. Because there was when I missed the bus station, I wasn't really, I don't really, because they don't actually, like unlike the bus in London where they actually tell you which station you're at, and then they don't announce which station they're at, so you just have to know when to get off.
I don't know.
I'm like, but I don't know, so I'm like very confused. Every time I ask the bus driver to alert me.
It's okay, you can do it.
But now at least she moved to somewhere different, like she's now working in a hospital.
Which one?
I have no idea, I think there's only one hospital.
Oh yeah, that's just one. Wait, which department?
Dentistry.
And I just started to get like,
It's a bit like,
What dentistry she did?
like just the general one.
The general. She going to specialise?
Maybe she's still considering, I think.
Do you want to I need a new one.
But then working in hospital needs on-call hours as well, so that's like, she said, usually she quite enjoy it, but then she said it's quite annoying when you have to wake up when you're sleeping halfway. So there's like a, yeah, if there's a patient coming in, then you have to wake up, there's no choice.
If she had A&E.
Yeah. This is gonna be really nice, like a fast.
I don't actually know.
But that's really far from actually, you know, it's just an hour more to do.
It's like tricky. I've done it. I need to change something.
Professor.
Yeah. So I was just asking him if it was right. Because it's about like protocol for not doing anything. I don't know if it's
But then the deadlines are so early.
And then I have the jeans deadline. So I need to go over my journal halfway through again. I've done the power. Yeah, like 4 times.
I haven't done that once. Yeah, because like no one initiated.
I initiated. I sent all the emails around.
Okay, so I'm just going to show you actually just. You want one last thing or 2 last things? I could go on all day, but who votes for 1? Who votes for 2? Excellent. There's at least 1 vote for 2. Okay. So yeah, it's about like the Brexit vote, really, isn't it? Same sort of percentage of votes.
all the electoral college votes.
Okay, so just suppose we were interested only in wanting to know what the amino acid names were. Right, so rather than the number of residues, we wanted to know how many, we just wanted a list of all the amino acids that happen to be used in this particular protein. So, let's just go back to this. Okay, so if I did this, I got the list of C alphas. So that was grepping for an atom at the beginning of the line in a particular file and piping that into the grep to get out the C alphas. So what I want to do now, and this actually wouldn't work on every PDB file because some of these fields can be wider than this, so they can end up touching each other, but we'll just assume that files are going to be kind of well behaved and not do that. So we're interested in this field, right, the amino acid name. So that's 1, 2, 3, that's the fourth field. So there is actually a thing built into Unix, Unix command line, called awk. And awk is not spelt O-R-K like the things from Harry Potter and the like. It is AWK, which stands, is actually the initials of the three people who designed it. Aho, Weinberg and Kernighan. Now awk is actually a little mini programming language which is designed for taking lines of data from a file and doing very simple manipulations with them, like extracting columns, counting things, that sort of thing. It's actually quite powerful, and I know how to use very little of it, but the bit that I do know how to use is how to extract columns. So we could take the results from this and do awk print $4. So it's single inverted comma, open curly bracket, and open curly bracket actually means do this on each line that you read from the file. Print $4, now this is one of the exceptions where I said most things count from 0 in programming languages, when you're referring to lists and arrays and things. This one counts from 1. So this is column 1, column 2, column 3, column 4. Close curly bracket and close single inverted comma. So if I do that, I just get the amino acid names. They're currently all kind of jumbled up. They just appear in the order that they appeared in the PDB file. So let's suppose we wanted to check whether this PDB file contained all 20 amino acids. Well, we could pipe this into sort. And sort, fairly obviously, just sorts them. Right? So we've now got, appearing on the screen, mostly valines, because all the rest have scrolled past. Obviously we could, as before, pipe that into less if we wanted to look through them. Has everybody kept up that far before I do the next bit? Okay. So awk is the clever bit that allows you to extract kind of fields. You can extract multiple fields, so I could do comma 4, comma 5, which would do 2 of the fields. You can also, by default, it separates on spaces, but you can tell it to separate on other things like colons or commas or whatever you want.
Yeah, how do you copy and paste?
How do you copy and paste?
From the previous line.
Just do up arrow. Just up arrow to recall the previous line, and then just move the cursor left and right.
If you actually want to copy and paste, you can also just highlight it with the mouse.
Yeah, you can highlight it with the mouse and click again. But
What do you want?
so, given that we've got a sorted list, what would we really like to do in order to find out whether we've got all the amino acids? We don't really want to have to go through this long list and check that all 20 amino acids occur. So if instead we do sort minus U, not only does that sort them, but it also uniques them. So if something appears multiple times, it'll only appear once in the output. And so now we do have a list that we could check that we've got all 20 there, but why not just send that into word count minus L for lines. And indeed the answer comes back as 20, so we know we've got all of the 20 amino acids there. So that's just introduced two things really, one of which was sort and sort minus U, and the other was awk to allow you to extract a particular column from a data file. So that was one additional thing I was going to show you, and the other additional thing I was going to show you was a little bit more complicated, because awk is kind of mini programming language. You can do things a lot more extensive than this. You could actually use awk to count the number of each type of amino acid as well. I personally wouldn't do it in awk, but you could. So the Perl programming language, which is my favourite scripting language, was actually designed as having all the abilities of awk, the command line, a bit of C programming, all kind of integrated into one package, and that's kind of why I like it, because it wraps up all the things that I tend to use anyway. So awk gives you a mini programming language. Actually, the bash command line is a mini programming language as well. So you can do some really quite complicated things on the command line. I mean, this is fairly complicated, the fact that we're linking together here, 1, 2, 3, 4, 5 different programs. Well, one we're using twice, but we're linking together 5 different commands. But we can do some really quite clever things. So, back in my PDBs directory, I have these 6 files. So I've removed everything else. I've just got my 6 .ent files. Now, just suppose you wanted to... Let's do something fairly simple first. We want to count the number of... just the number of lines. We won't bother with all this complicated bit. We'll just say, how many lines are in each of these files? Okay, so we could do word count star.ent. Or word count minus L star.ent. So that tells us what we want to know. We've got 7,538 lines in that one, etc. Total of 21,803. So that's useful, but I'm just using counting the lines as an example of the sort of thing you might want to do. Suppose, in fact, what you want to do is process every one of those files, do something with it, maybe it's counting the number of C alphas or whatever, and you want to produce an output file associated with each input file. Perhaps it's, extracting the sequence. So, little program that I've written called PDB to PIR, which I mentioned earlier, which will do exactly that, it will extract the sequence data. So for each of these .ent files, we want to have another file called .pir. That's a kind of realistic thing that you might want to do. I'm just going to do a simple thing, because you've got the software to do it, of wanting to have a .wc file which has got the word count for each of these. So for pdb9aat.ent, there'll be a pdb9aat.wc containing the number 7538. So obviously you could do word count minus L PDB9AAT into PDB9AAT dot WC. And we have a look at that. And it's got the information that we want in it. But that would be a bit of a pain if you had to do that, in this case, 6 times. But imagine it was the whole protein data bank with about 100,000 entries in it. You don't want to have to type that 100,000 times. So what we do is, let's just remove that WC file. Instead we type for file in star.ent. So do you remember when we were looking at the kind of fundamentals in Python programming? The idea of command loops and things. We could do for I in list. This is the bash equivalent of doing the same thing. So our variable is called file, and we say the word in, and star.ent is our list of all of the PDB entries. So we can say for file in star.ent. In Python we had to have a colon, and then we had to indent the next line to indicate the start of the kind of block of commands that we're going to run. In this case we don't. We say do. That's how we start our block. So we're stepping through each of the files, and we're going to do what's in this block. So we start with do, and we say WC minus L. Now we want to do it on the file, this particular file that we're working on. So we say $file. That means take this file name that we've got here and kind of expand it out into what its actual file name is. I'm just going to do that for the moment. Then I'll say done. So that's the end of the block. And there you can see it's now run this WC program on each of these in turn. Right, but it hasn't done anything else. It hasn't put the answer into another file, which is what we want. So let's just do this again. So for file in star.ent, do WC minus L $file into $file dot WC. So now instead of displaying on the screen as we did here, we're doing WC minus L $file and send the result into $file.wc. And done. And you can see it's obviously sent the answer somewhere. It hasn't appeared on the screen. And if we do an ls, you can see we've got, for every .ent file, we've also got a .ent.wc file. So we could have a look at one of those. And we see the count in there. That's not quite what we wanted, because we've got .ent.wc instead of just .wc. Doesn't particularly matter, as I said, extensions are arbitrary, but it's kind of nice to stick to a convention. So it's going to introduce a rather useful little command here, which is base name. So if I type base name pdb9AAT.ent, it doesn't do anything very exciting. It just replies with the name of the file. But if where am I? So if I did also base name gave a whole directory, before the name of the file, still just gives the name of the file. So base name gives you the basic name of the file, stripping off all directory information. Now it also, if I go back to this one, if I specify an extension after it, it will strip that from the name. So base name something.ent followed by .ent will strip off the .ent and just give you the file name itself. Right, so we've got a command that would allow us to extract just the basic name of the file without the extension. So we can actually exploit this in our loop in order to get a better name. I'll show you how we do this. So we say for file in star.ent do wc, actually before we do this, so just Control C to break out of what you're doing. I'm going to remove the .wc files that we've got at the moment. Okay, so for file in star.ent do word count minus L $file, and I want to send it to somewhere. Now I want to send it to the file which is the base name of our current file. So our current file maybe is pdb9aat.ent. So I want it to be pdb9aat.wc. So I can use this base name command to extract the first bit of the name. But to do this as part of this, so we're actually getting the text rather than sending this to a file called base name, I put it in backticks. So it should be the top left of your keyboard somewhere, like an open single inverted comma. So backtick, let's put base name instead of base name. Backtick base name $file.ent means run this command and redirect it to whatever comes out of this command rather than redirecting it into a file called base name. Now we actually wanted to add WC on the end as well, so I'll add the WC there too. And then done. And what we should end up with now is, yes, for each .ent file, we've got corresponding .wc file. So this may seem a bit complicated and fiddly, but it's actually immensely useful when you want to do something, as I said, like work your way through 100,000 PDB files or 100,000 files with sequence information in them and run a program on them, get the results into another file, and you want to leave that running over the weekend so that you don't have to do any work over the weekend. This is the way you do it. So it's basically for file in and then your list of files, do some command, done, and in this some command we're doing a little bit of kind of clever stuff to give us an output file name which is relevant for our input file name. Okay, so everybody managed to recreate that. So these slides will be, so the slides that I used from the talk bit will be available on Moodle if they're not already. And those slides actually have some kind of basic Unix commands in them, what I'll also do is another useful command for you, history, just lists for you all of the commands that you've used recently, the last 1,000 commands or something. So I will put the history of what I've just done into a file. I'll edit it slightly to remove mistakes and stuff that's not relevant, and I'll stick that up on Moodle as well, so that you've got an exact copy of the stuff that we've gone through. Do you have a question over here somewhere? A hand? Yeah. You've got
I managed to stop biting my nails.
Yes, I do.
I've kind of gone down the side.
Yeah, enter.
But these are okay. Just look at these. And even that.
I'm getting all this last part.
I just buy this game.
It's just to see the picture that I've done before.
That's alright. That's
Sure. Yes.
yeah.
Because I'm usually compare why I want to do.
Right, we got.
So it's done?
Yeah.
You have to save it or what?
No. No. Dying. Yeah, so I haven't eaten since 8:30. Oh my god. Do you know what? Close.